welcome and good to see all of you in one of our Saturday Science series. Now, in the last months, you have heard many of my colleagues from the physics department speak to you. For instance, in November, you heard Dr. Matthews tell you about using X-rays and magnetic phenomena to look into our bodies, so imaging inside the body using X-rays. Earlier, you heard about gamma rays from lightning, and you heard about the physics perspective that you can have about sports like football, LSU football, or baseball, and so on, all very topical questions around us. And today, I thought I would give you a slightly different way, and that is, what is it that really unites all of us in physics? And the subject of physics is really a way of looking at, of course, at the world around us, the physical world, and we look at it with a particular aspect and a particular approach, well, some very simple themes and principles. And so I sort of want to use that to say it's seeing the world with our physics eye. So how do we do this? And I'll try to give you a little flavor of what are some of the basic ways that we approach the world around us. And I mean very seriously the word our, because really all of us can do it. It doesn't have to be professional physicists. Of course, someone like Dr. Singh or I, we have our professional areas within the field of physics where we are doing research on some very specific subjects and subtopics and so on. But really what unites all of physics and in some ways gives a coherence to the whole subject is that we look at the world around us in a certain way of looking to understand what things are. So we all, of course, are looking at the world around us. We live in this world, and this is why I say all of us can train ourselves to do things like this. So for instance, of course, we look through our senses. So we certainly see visual patterns in the world. We hear, and so we have audio and oral patterns. Then we have the other senses. But ultimately, of course, the meaning is how it's interpreted in the brains, and you put all these things together in some ways. So take a very simple thing like a rose. I think even if we are not professional horticulturists or biologists, pretty much all of us know how to recognize a rose. And a rose is somehow distinct from some other, say, a chrysanthemum or a marigold. So there's something just in the visual way that there are, of course, enormous numbers of varieties of roses, but we have a way of thinking about what it is to mean by a rose when we think of it visually. Now, of course, we also know that we associate a certain scent. So again, the essence of a rose is in some ways also in its smell. There's the famous line of Shakespeare, a rose by any other name would smell just as sweet. So all these things together are, of course, things that are then finally interpreted in the brain. And so physics eye is really the same thing. It's something inside that we can bring to bear when we look at the world around us. And so I'll try to give you a little flavor, as I said, of how this can be understood by really anybody. So all of you can do the same thing when you look at the world around us. Now, Dr. Singh mentioned that I had a book recently which I called The Beauty of Physics. And the idea was, in fact, to take a few themes. I've just listed them here. These are the names of the chapters. It's not important for my purpose here. I'll just take two of them. The first one, which I called Adding a Dimension, and something called Saddles. And I'll use this to bring out the aspects that I mean when I say that we look at the world through a certain way of looking for patterns, and that is what I mean by looking through our physics eye. So let me start with a very simple thing. Now, many of you, some of you are probably bird watchers, but even if not, we certainly see birds around us. And here are two birds that some of you will probably recognize. There's a wading bird, which in fact you will see in Louisiana in marshes and so on. It's called the stilt. And then there's the flamingo. You don't see it in Baton Rouge, except perhaps some pink flamingos, plastic ones that you will see in the lakes. But all of you, I'm sure, have seen pictures, if not seen in zoos, flamingos. And the thing that strikes you immediately, of course, when you look at this, is that these are two birds which have a kind of living that they make, their habitat. They wade around in water. So in some ways, immediately, you will yourselves all say that we understand why they have these sort of long legs, which is the first thing that strikes you after their color and their specific shapes. Now, the stilt is a small bird. In fact, this is somewhat enlarged relative to the flamingo. The stilt is a bird which may weigh about 120 grams, a quarter of a pound. It's like a stick of butter in a 4-pack of butter. Whereas the flamingo is a much bigger bird, a few pounds, say 4 or 5 pounds, or 2 kilograms. It's, of course, a much bigger bird. Now, if you look and measure their lengths, for instance, in fact, many birders do that. They measure things about a bird. If they are, for instance, catching a bird and banding it or so on, they measure things like lengths, they measure the weight, and then today they might take a little blood sample for a DNA sample and so on. But the typical thing we think about is, for instance, the length of the legs. As I said, clearly this is a smaller bird. It has 8-inch legs, whereas the flamingo, which is a larger bird, has 20-inch legs. Now, all of us, of course, immediately will be thinking like this when we think about patterns that we see around, in this case, the pattern of 2 birds. Now, the physics eye that I want you to sort of think about is that if you think now in terms of the dimensions of the bird. Now, clearly, there are some things we are talking about which have length, like the length of the legs, and that's what I said was 8 inches for the stilt, 20 inches for the flamingo. That's about 2.5 times the 8 inches for the flamingo. Now, if you look at the weights, similarly, the weight here was 120 grams, whereas this is 2 kilograms, or 2,000 grams. So that's about 16 times as big. And now, all of you will immediately understand when I say that the weight, after all, is something which has to do with the volume of the bird, which has 3 lengths in it. We think of length, breadth, and height in our typical way of thinking about our 3-dimensional world or a depth. But the main point is that there are 3 lengths. So it's as though you multiply 3 lengths, and in our notation, we'll write it as length cubed. And so you see that indeed, these numbers are not independent. So if you take 2.5, which is 5 over 2, and you take the cube of it, that is indeed of the order of about 16, which is the ratio of the weights of the birds. So a little bit of thinking like this in terms of what we call dimensional thinking. In fact, that's one of the first things that physics students learn, that you think in terms of what we call the dimensions of the world around us. And so it seems very natural. And now it brings also another element, that the physicist who is looking at this, these are completely different biologically. They are different species. For a biologist, there are other things that are of interest about a stilt or a flamingo. But for all of us, we can immediately see, after all, they are governed just as much by the laws of physics as anything else. And therefore, it is not a surprise that if the lengths of the legs scale by 2.5, then the weights scale much larger than that. In fact, the cube of 2.5, which is about 16. And so this is what I mean by saying that you can look and see a little more into the pattern, also bring in some numbers. So we think in terms, quantitative terms, not just qualitatively say, of course, this is the bigger bird, so it's heavier and it's also longer, but a little more quantitatively as well. And then when the numbers sort of fit together and seem to make sense, that is the sense in which I say I'm looking at it with the physics eye. Now, all of us, as I say, have that, and we can all look at things with the physics eye. Now, something very similar, of course, is again something you're all familiar with, and that is that when a newborn baby, so either one in your family or a friend's has a baby, besides, when you get the announcement, besides the name of the baby, you'll usually say something about the length and about the weight of the baby. Now, of course, these will be individual. Every baby is different and unique, and so there will be something specific. But the interesting thing is that, again, if, for instance, you were to Google, or just by experience, you know the rough range of the length of a newborn baby is about 18 to 22 inches, let's say. And similarly, if you look at the weights, a small baby is about 5.5 or 6 pounds, a larger baby maybe 7, 8, 9 pounds. And in fact, on Google, if you look at the range, you will get numbers like this. Now, again, I want to draw your attention to the fact that that spread, of course, there are a few which will lie outside this range as well. There'll be some very small babies, smaller even than 5.5, certainly some very premature babies will be. There may be a few babies which are born much heavier than the 9, let's say 10 pounds, but the rough range, which will cover nearly all babies that are born, and again, it doesn't matter where in the world, they lie in this range of lengths and in this range of weights. And now what you notice is that if you just look at the range, as I said, if you were to Google length of a baby or weight of a baby, these are the numbers you get. So from 18 to 22 inches, that's about a 20% range. So if you take 20% more than 18, it's 22. So it lies in about a 20% range. Look at the weights. Similarly, the weights 5.5 and 9, that's now 60%. Now, that again, immediately from the physics side, is, notice that's a factor of 3, which is just what you would expect. That if the lengths have something which carries a 20% label on it for the range, then the weights will be 3 times that. That will have a range of a 60%. So in some ways, again, you don't really need to specify both the length and the weight. You pretty much have an idea of the other once you see it. Now, this is part, again, of physics. We try to see things from different points of view. We try to condense them and sort of zero in on the essence of what is the phenomenon that we are talking about, in this case, some very simple things like lengths and weights of birds or babies. Now, of course, I can carry this further, and there's even more to this, because it's not simply in terms of the overall lengths, weights, and numbers like that, and the quantitative thing, but if you think of the structure of organisms. Again, this is a biological example. These are our lungs, and these are our intestines. And now everybody is familiar that when you look at them, you have this structure, for instance, of lots of folds. The intestine is something which is built up of many, many different folds. If you were to stretch it out, it would be much taller, much larger than our own size. Or you look at the lungs, there are all these little branchlets of the airwaves and the blood circulation. And so, again, in a way, it's immediate that this is how it should be, because if you think in terms of the surface and the volume of any object. Now, a surface is an area, so when we talk of an area, for instance, so many inches or so many miles on one side and another side. So when you measure areas in square miles, or you measure areas in square feet, or so on, a surface is built up of 2 lengths, so a length and a breadth. Whereas a volume is, of course, as we just said, of 3, so it's a cube. So, of course, when you go from something smaller to something larger, there is more surface, there's also more volume, but what is interesting is that the ratio of the surface to the volume actually goes down. So a larger object, scaled up from a smaller one, actually has less of a ratio of the surface to the volume. In fact, that ratio will go down, and so we put this -1 simply to indicate it's 1 over the length, the exponent, and therefore the surface to volume is actually larger for a small baby than from an adult. And so, for instance, again, every parent knows that little babies, infants, can chill much more, and that's why you sort of bundle them up much more. They are, of course, smaller. The surface is smaller, their volume is also smaller, and so on, than the adult, but the surface to volume is actually larger for that baby than it is for an adult. And therefore, you have to be much more careful about things like, because after all, you chill or you gain from the surface, whereas what you really depend, your metabolism depends on your total volume. And this is the reason why organs like lungs and stomachs and intestines, which have to do this, of absorbing nutrients, absorbing oxygen, and so on, these are going to be very fragmented looking, so to say, or folded up, so that you can get a larger amount of the surface which you're interested in for that particular volume that you're packed in. In fact, a 19th century physicist called Darcy Thompson had a beautiful line when he said that the form of a body is a diagram of the forces acting upon it. So simply from knowing the context, knowing the forces that are involved, in this case, knowing the absorption aspect as against the metabolic aspect, and one is going like surface, one is going like volume, the physics eye would say that you would, in fact, expect structures so to also reflect this idea of the surface to volume ratio. Okay, now let me go on a little more. And now this is actually the part of what we call dimensional way of thinking. So the very first thing is simply the usual dimensions that everybody is familiar with. We live in a three-dimensional world. There are three independent directions or dimensions. Now, for a physics perspective, they're all lengths. Doesn't matter, one is a breadth, one is a height, but they're all lengths. So I can think of lengths, length squares, length cubes, and so on. Now, the next thing of dimensions, of course, is that there is time. Now, time is something different, and time is also, in that sense, like a basic dimension. So we enlarge our meaning of the word dimension from ordinary language to say that we'll also think of things like time, for instance, as its own dimension. So, of course, I will think of it, I'll always denote dimensional quantities in red with this square bracket. So time is something different from lengths or length squares or length cubes. But as soon as we talk about any motion, of course, it's a motion in terms of displacements in space as a function of time. So I have to use both. And of course, a speed is always some length divided by time. It may be miles per hour here, it may be kilometers per hour in Europe, it may be feet per second, whatever it is, it's always some length divided by a time. And so now take a very simple thing. In fact, we are all used to knowing about pendulums. So here is a pendulum. A pendulum at its basic is simply a length of a string, and there's a little bob of some kind of mass. And the idea, of course, is that when you swing it, it swings in a very rhythmic, what we call a periodic fashion. And so, in fact, you can use that, if you wish, for actually measuring time. This is, of course, how grandfather clocks and the first measurements of time came about. Now, if I have a pendulum like this, now, of course, physics students study how to write down the time given the length, but you don't really need very much to understand. There is one formula here, and that formula simply says that the time period, because, of course, this is all a rhythmic motion, so it goes from one end to another and comes back, and that swing time is given by an expression. Now, that expression, how it's derived and so on, and Newton's laws, all that kind of thing is not really relevant for what I want to sort of point out, that after all, if it's a time, then it has got to depend on obvious things that I know. There's a length, clearly, of the string. Clearly, if I took a smaller length, then, of course, it'll swing faster. And so the time period is going to be something which will depend on the length. And what else does it depend on? Well, of course, it's swinging because of gravity on Earth. So there is this famous thing called acceleration due to gravity that certainly every layman also hears about, and that is the rate at which a velocity itself changes. Acceleration is, after all, that. In your car, you can go from 0 to 60 miles per hour in, say, 20 seconds. So it's so many miles per hour per something else seconds. So it's always a length divided by 2 times. So in fact, the value of the acceleration due to gravity, many of you students will know this, is of the order of about 10 meters per second squared, or 30 feet per second squared. This is a meter stick, so it's about 10 meters per second, because it's a length divided by 2 times. And from that, immediately, you can say that if I want to form something which has dimensions of time, I would take the length, divide it by that little g, which is a length divided by 2 times, and if I then take a square root, that will, of course, be a time. And indeed, that is the expression. You can derive it in any number of ways, but the time period of a pendulum is essentially just the square root of the length of the string divided by little g. Little g is the same everywhere on Earth, wherever you are, and so the time period is simply a question of the length of the pendulum. So a grandfather clock will work just as well here as it will work on the other side of the world. Now, there's a 2 pi, which also you will see has to do with the fact that we measure angles in physics, not in the usual way we think about in layman terms of degrees, but we think of it as a ratio between the arc of the, for instance, in this case, the pendulum, divided by the length. And it's something that, again, students here who have been introduced will recognize. We measure it in radians. And so that is what is involved in talking of angles. And pi occurs in describing that, because we take a full circle. I'll get to this in a minute. The circumference of that circle is an expression that many people know, is 2 pi times the radius. So if you divide by the radius, there is that 2 pi. And that is how it shows up here, and you will see a little more of a feel for why this is there. But those are just pure numbers. Pi is a little more than 3, as you know, so there's a number of 2 times 3 in front. But the essence is that it's a square root of L over G. And now, the other thing that I said about physics I is that we always think of specific numbers, so we get to more quantitative pictures of the patterns that we are seeing around us. So now let's do that. So here's a meter stick. Now, our own bodies are about a meter. So our arm length is about a meter. Our leg is about a meter. So if you take an adult and I walk across, after all, it's like a pendulum. You're swinging your leg, and gravity is what is bringing it back. And so indeed, you would say that the time period will be involved in how fast or how the rate at which I can walk. And in fact, think about it, that if you take a 1 meter, which is, as I said, roughly the size of an adult, so a 1 meter, then, and I divide by g, which is about 10, that square root is almost of the order of 3 in the denominator. So it cancels out that pi, which is roughly that. So it gives you about 2 seconds. So in fact, you get now a fairly good estimate for what is the time period for a meter length pendulum. And so that is the same, after all, that's going to be involved when I walk. And I'm covering how much? I'm also covering of the order of a meter when I walk, because I'm swinging through a meter. So 1 meter divided by 1 second, which is half of the swing, is the typical rate of a walking speed. Now, of course, I can convert it immediately, because there are 3,600 seconds in an hour, and 1,600 meters, or 1.6 kilometers, is a mile. So 1 meter per second is the same as about 2 miles per hour. And that's a pretty good estimate, quantitative estimate of what would be the walking speed. And as you can see here, you can get to it by just thinking in very simple terms of just the dimensions that should be involved, things like length and time, because there is a speed involved, and an acceleration, and that's a fixed acceleration around the body. And so that gives me an idea of the kind of typical walking speeds. Now, of course, when I run, I can run a little faster than that, but walking speeds are of the order of 2 or 3 miles per hour for most people. Okay? Now, interestingly, you can actually think of some things which are not immediate like that. Now, many of you have lived through, in past years, these tsunamis that occur. There was a fairly famous one of the Japanese earthquake. There was one a little earlier after an Indonesian earthquake. And these tsunamis hit parts of, for instance, India and Sri Lanka and Indonesia. And these tsunamis are these incredible, powerful waves of water which are triggered when something happens, say in the ocean floor, there's an earthquake and there's a slip, and that generates these waves. Now, there's a very lot complicated things going on in here, but now let's just think whether I can think about why is it that a tsunami seems to travel at almost jet plane speeds. Tsunamis are known to go across the Pacific Ocean or across the Atlantic Ocean in just a few hours. So they're going almost at the jet speed. And to get a feel for that, again, I will say that after all, when you displace something, like you suddenly jerked the ocean floor and you displaced a huge amount of water. Now, that water will, of course, settle down, because gravity will pull it down. So again, I would expect that little g is going to play a role, because that is what is going to restore to the balance. And so now again, I ask, if I have a little g, which is a length divided by 2 times, and I want to get a speed, what would I do? I would multiply it by another length and then take the square root. So if I have a g, if I multiply with something which is of the order of a length, and I've used the symbol here, which physicists will recognize we use for a wavelength, that's the wavelength, which is also of that same order, but all of it has to do with the fact that the basic average depth of an ocean is of the order of 2 kilometers. So if I use a number like 2 kilometers for that length, and I use little g, and again, I just do a very simple calculation without any complicated hydrodynamics and all the physics that's involved and the geology that's involved and so on behind this tsunami, you will get not 1 meter per second as I got for my walking speed, but I'll get something 150 times larger than that. So instead of 2 or 3 miles per hour, you see now why tsunamis actually move with this incredible speed as well. Not only is there a huge amount of water in that wave which is coming, and those of you who saw those pictures of Fukushima and the tsunami that followed it, it's really impressive how it completely destroys, of course, everything in its path. And it also goes extremely fast. As I said, they travel with almost jet plane speeds. But again, you see here how, by thinking of it with a kind of physics perspective or a physics eye, I can actually make sense of this with very simple terms. I've used nothing really more now than what I did when I talked about a pendulum or I talked about a walking speed. Now, that's the other part of the beauty to me of physics. It's to see patterns of things which at first sight look like they have nothing to do with each other. My walking speed or the tsunami's speed, what does it have to do with one or the other? But you see, by thinking in terms of dimensions, you can actually get a very good estimate, even quantitative, semi-quantitative estimates of what is going on. And this is what I mean by saying that the idea of thinking in terms of dimensions is very crucial throughout any physicist's way of thinking. Let me give you one more example of this, and that is that, of course, I introduced a length, then I introduced length squareds and length cubes, and then I introduced speeds and accelerations by using lengths and times. And the essence of it is simply there's something of the order of a length, and then there's something of the order of a time. Whatever that time is, whether it's a second, whether it's an hour, but it's a time. Now, one more thing I need when I think in terms of energy. Now, again, many of you know, of course, that when, of course, I'm moving, I have some energy, and that's why, in fact, I can move. If I have something which is placed on a certain height, and then, of course, it has more energy, which is why when I let it go, it can come crashing down and hit with some speed. Now, again, even the young students know that, for instance, there are 2 types of energy, at least, that we immediately think about. One we call energy associated with motion, which is kinetic energy. It depends, of course, on the mass. Clearly, a 10-ton truck, even when it's moving slowly, has much more energy than when I am running as fast as I can. So it depends on the mass involved, so that is another. Now, this has nothing to do with lengths or times, so that's a new dimension. So I've used the word dimension in this sort of metaphorical sense. That's a new angle, a new dimension, which also even metaphorically in English we use. We talk of a person having many dimensions to him or her. And so this is the same sense in which now I introduce the mass, and you can see that the kinetic energy, there's a half, which is not very important here for our consideration, but it involves a mass and it involves a speed squared. So of course, when I move faster by a speed gaining by a factor of 2, my energy actually goes up by a factor of 4. It's 2 squared. It doesn't just scale up with the speed as v, but it carries a v squared. Now, the potential energy is simply the fact that near the surface of the Earth, depending on how high you are away from the surface, there's also some energy stored. This is the whole basis of how we use water power for generating energy. So if you have a waterfall and you put a little turbine at the base of the waterfall, then that potential energy which is being brought down by the water that is going to spin your blades then can generate electrical energy. So you can convert one energy into another. Now, what is important, however, again from the dimensional view, the dimensional eye, is that dimensionally any of these expressions, you can think of all other kinds of energy, electrical energy, heat energy, nuclear power energy, doesn't matter. All energies will be a mass, and it will be a length squared divided by a time squared. Now, that's immediately obvious for that first example there, but it's true for every one of the others, as you can immediately check. And indeed, that is dimensionally what the energy of something is. So with that now, let me introduce you to a question, which is, we've all seen pictures of explosions. So for instance, maybe a gas main that exploded, and then we see on our TV news, there's this huge fireball, and it sort of expands, of course. And then, of course, the granddaddy of them are these nuclear explosions, these nuclear bombs, and this big mushroom cloud, which then expands in some manner. Now, let me ask the question, for instance, how fast does an explosion like that spread? So what is the radius of this fireball, the length? So there's a length involved for the size of that fireball. How does that scale with what should be important for this particular problem. Now again, the actual working out of any of these problems in any context may be very complicated. It may require special physicists and engineers to be able to work out exactly what is going on in each of these instances. But all of you can immediately follow me when I say that it will certainly depend on the energy. Because certainly if I have a larger explosion, then of course it'll spread out much more. It'll certainly have something to do with time, because of course it's going to spread at a certain rate. So if you wait longer, of course it has spread to a further distance. And it'll finally, you would expect, have something to do with where the explosion is. If the explosion is in air, it's after all pushing against air. So somehow the density of the air is going to be relevant, because if I exploded the same thing under water, then of course it will not have quite as much spread, because water is denser and it's going to resist the expansion more. So I would expect that the density will also be involved. Now the density is of course a mass in a volume. So in our terms, it's a mass divided by 3 times. And now all you need is to look at these things in red that I've written of how masses and lengths and times are involved in these things to see that the only way you can construct something which has a dimension of length, as we would say, out of energy, time, and density is to form this particular combination. Now, this is a fairly involved, fairly sophisticated. You will see powers, including a 1/5 power. So it's like the 5th root that you have to take after you take the energy, multiply by the time twice, time squared, divided by the density. Now, as I said, the actual hydrodynamics involved in these explosions and so on can be quite involved to be able to calculate something like this. But you can be pretty sure there is a number that I put here, which is usually something which doesn't have dimensions. We say, well, it will be some number. It may be 2 pi that we saw in one case, 1, and numbers like that. But really the important thing is that it will involve energy, time, and density in this way. So notice in particular that, of course, as energy increases, it's going to take longer to reach a certain radius, as time the same way. And if density is smaller, then of course the radius increases faster. But it only goes like the 1/5 power of the density. Now that is very interesting, because the density of air, as we know, is very, very small compared to the density of water. It's about 1,000 times smaller than the density of water. But it doesn't mean, as of course qualitatively I would say, clearly in water it won't expand quite as much, because it has more to push against in terms of the denser water. But I can say a little more about it. It actually goes like the 1/5 power. So it doesn't go down by 1,000. It actually goes only by the 5th root of 1,000, which is only about 3. So the number is only about 3, because 3 raised to the 5th power is of the order of 1,000. And that's a fairly sophisticated answer to get out of just very simple thinking in terms of just the dimensions of what could be possibly involved in this phenomenon I'm talking about. So that is, to me, another example to show how all of us can train ourselves to think like this in terms of dimensions when we look at patterns around us, and we'll make a little more sense, if you wish, of what we would first see from just the immediate visual sense of what we have observed. Now let me move to the next step, and that is something that I want to introduce, which is another concept which I find as a very common theme throughout physics, including some very sophisticated physics of the kind that our chairman here, for instance, works on in general relativity, the theory of Einstein's for gravity, and so on. But what it is that many times when we are thinking of a physics problem, it turns out to be simpler to think of it in a higher dimension. Now, this might actually seem counterintuitive at first sight, that if I have a problem in 3 dimensions, why do I go to 4 or 5, which would probably complicate matters more? But actually it isn't. It actually simplifies matters. And that's a theme that I like very much, and I'm going to talk about that in a very simple context again, and that is the context that I started with of something like a pendulum and the swing. Now this is what physicists call a harmonic motion, because it's like a harmony. It sort of has a periodicity to it, and it's called the simple harmonic motion. It's the simplest of such motions that we study. Now the simple motion in a line, so if I were to think of this, of course it's a slightly curved line if it's swinging in an arc, but it's still a line, or it could be for all practical purposes, just along a line. A simple motion in a line where it starts at 0, goes to some extreme, and then comes back, swings through that 0 as it goes to the other extreme, and swings back and forth. Now, that's the motion of this pendulum, and you saw that expression for the time period that we had for this simple harmonic motion. Now, interestingly, instead of that motion, which is actually in just one line, which is one dimension, if I think of it instead in terms of a motion of an object which is moving around in a circle with a uniform speed of rotation, uniform what we call an angular speed by which it is moving around, then if I take the position, say the red ball at its extreme, and I just think of it projected down onto this axis, you can see that as that ball moves around in that circle with uniform speed, this object is going to do that motion that I've just been talking about. Now, this one-dimensional motion is not complicated. Simple harmonic motion is one of the simplest motions we can study. But in some ways, that motion is even simpler, because even the radius is fixed. That red ball is always at the same radius r from the center. It's also moving at constant angular speed, omega. So both the radius and the frequency of the motion are fixed. Whereas here, the frequency is fixed at that time that I gave you, but the amplitude is changing in some rhythmic fashion, and I'll get to that in a minute on the next slide. But you can think of this motion as associated with this even simpler motion in 2 dimensions. And that is the kind of thing which I mean by saying that there's a theme of now adding a dimension. So this is going a little further than what we just talked about of just the basic dimensions of length, time, and mass, but now I'm introducing this idea that I can add a dimension and somehow get either more intuition or more insight or maybe a simpler picture of what I'm saying. And now, in fact, you can see why that 2 pi came in. 2 pi is a way of saying 360 degrees. So, of course, the full motion has something to do with an angle that is going around a full 360 degrees, which we call 2 pi in these radian terms that I talked about. So everything about that initial simple equation, incidentally, that pendulum equation to me should be one of the famous equations. So generally, when you ask a layman what's a famous equation, they'll say maybe Einstein's E equals mc squared. Or they may say Newton's F equals ma. Now, those are indeed extremely important and famous equations. But I would say that the pendulum equation, that the time period is 2 pi square root of something divided by something, is as important an equation, if you wish, if you were to ask what is the most important equation in the world. But anyway, getting back to this, now let me just say the same thing slightly differently in the next one, which is again, just forget about the top here, that this motion in a circle, if I think of it instead as projected on, say, the x-axis, that motion is the motion of the pendulum, or a periodic motion, rises to a maximum, dips to the minimum, then comes again, and that would be a full time period. But that full time period is simpler to think of in terms of something which is rotating constantly with constant radius. Now, of course, I can project this onto the other axis, and instead of this, which some of you will recognize as what we call a sine wave, that will be what is called the cosine wave, which is just 90 degrees out of step, so to say. That when this is a minimum, that will be a maximum, but it's the same thing, just shifted in degrees by 90 degrees. Now, the same thing, incidentally, I can now stretch a little more and say, take this famous problem. Physicists recognize this. Generations of students study what is called a tunnel through the Earth. And the idea is very simple. For those of you who haven't heard this, the idea is the following, that if I take the Earth, let's just imagine a big sphere, and I drill a hole, say from Baton Rouge, right through the center. Of course, I'm not going to worry about technologically and so on. It's going to be very complicated till it emerges on the other side of the Earth. Now, it's a very simple thing to understand that if I drop a ball now into this tunnel, which has been drilled through the Earth, it's going to go there, and it'll keep doing that oscillation, just like my pendulum. And the time period of that is what? Well, let's do the simple calculation. Again, I would expect that gravity is coming in. So little g is there. And to get the time, all I need is a length. And what would be the length that I'm talking about now? The length would be something like the size of the Earth, say the radius of the Earth. So put another way, if instead of a 1 meter pendulum, suppose I were able to stand somewhere way out in space with a 6,400 kilometer pendulum, and then were to look at its swing, that time period is going to be exactly the same time period, because that's all that is involved. There is a length, a radius, and there's little g. And indeed, if we put in the numbers now, of course, I still have the same g, but instead of just 1 meter, now I have 6,400 kilometers. If you put that number, you get about 84 minutes, or about 1.5 hours. That's indeed what would happen. If I were to have such a tunnel, and I were to drop something, then it would go back and forth in about 1.5 hours for a full time period. Now, it takes just another stretch, and this is again the physics eye, that instead of going down through the Earth, suppose I thought of a satellite which is in orbit right around the surface of the Earth. Now, most of our satellites, as you know, including the space station, is not that far above, so that it's pretty much about the same distance from the center as the radius of 6,400 kilometers. So that's why it's the same number. So the International Space Station goes around once every 1.5 hours. And of course, some of you may have seen it, because it's a bright object that you can sometimes see in the sky, and it goes around in a periodic way of 1.5 hours. So you see again here, this has connected something as simple as a simple pendulum here to something like this concepts of whether it's a tunnel through the Earth or whether it is a near-Earth satellite, as we describe them. Of course, the further out you go, the satellites will take longer. Finally, the moon, for instance, which is much, much further out, takes, of course, a full 28 days to go around. Now, this connection between the one-dimensional motion and this added two-dimensional motion also arises and has technological applications. Now, any of you who have seen a locomotive, particularly in the old days, when you could see clearly abreast the picture of the wheels and how these things are moved by a piston, which is, of course, being driven in this case by a steam engine, and it goes back and forth, and there you are converting a one-dimensional motion into the circular motion of the wheels. And so that's an example of this added dimension connection between one and two-dimensional motions that I just talked about. It's actually, as a philosophical thing, it's really very interesting. You are converting a one-dimensional motion of that piston, the same thing with the pistons in our cars, of the older cars, not the Teslas, and it's converted into a two-dimensional motion of tires and wheels, which is then converted back into a one-dimensional motion. You can go hundreds of miles in some direction on the train tracks. Okay. So there is this interplay between the one and two dimension. I could, of course, go on with many more examples. I won't, but just to mention, for instance, you've all heard of Einstein's theory of relativity, and that we think in physics of space and time as really somehow sort of put together. And indeed, that is, to me, another example of this kind. That motion in three dimensions space, three-dimensional space, some ways you get much more insight, and you get a much better understanding of it when you adjoin another dimension. In that case, it's the dimension of time. Okay. So there are many, many examples of this kind, and this is what that book that was mentioned will go into, just to illustrate how many different types of physics problems you can integrate under this theme of adding a dimension. Now, to introduce the next topic, I'll say a few things about the second topic of the saddle. Let me just go back to the pendulum. And there is a way of talking about this. I've already talked about potential energy. And it's actually just to say that in some ways, what is happening for the potential energy is it looks something like this parabola. Now, those of you who know a little more know that the parabola goes like the square of the distance. So this is a parabolic shape. And of course, if I turn it around, that would give me something which is a three-dimensional one, like a parabola. So like telescope dishes and so on, you have a parabola. Now, if I have a parabola, we say that this is something like a surface on which things are moving, whether it's the pendulum I'm talking about, it could be springs, it could be very different things, but they can all be unified in a picture of having something like a parabolic bowl. And if I drop a marble, you see that what it does, it goes back and forth, And that would be like the motion of a pendulum. There's a simple harmonic motion with a certain time period, which keeps repeating. Now, that, of course, finally, we know that friction and so on will slow it down, and it'll come to a stop right at the bottom of the parabola. Now, if instead I took this and I inverted this, now what would we expect would happen? Now, clearly, I have a parabola, but it's sort of the upside-down pendulum, if you wish. So it's like a pendulum which is standing up instead of hanging down, and we know that that's an unstable situation. Even the slightest disturbance, of course, it's going to fall off. It's not going to keep doing a stable motion like the pendulum. Same thing, if I place this marble here, of course, it immediately runs down the parabola in some direction. Now, with that, let me introduce the idea of a saddle. Now, again, saddles are things which we're all familiar with. Certainly, we think about a saddle that you put on a horse if you want to sit on the back of the horse. But the other way we think about saddles is, of course, in mountains. Now, a little less familiar in Louisiana, but I'm sure many of you have gone hiking in mountains, and you have encountered what is called a saddle. And a saddle is typically the one that you would sort of climb to when you go from one valley. If you want to go to the other side, to the other valley, so to say, you go through what is called a saddle. And what is a saddle? A saddle is in one direction. You're sort of climbing up to some peak, middle point of the saddle, and then going down. But in the other direction, you're at the bottom of something which is a peak on one side and is a bottom. So it's a combination of the parabola that I had here in one direction and the upside-down parabola in the other direction. Now, of course, if I had such a saddle, again, I would not expect complete stability right at the middle of the saddle. Of course, in this situation, it's quite flat. But in most situations, when I have a sharper point, then, of course, I would expect that immediately on the unstable direction, the marble will lie down, will just flow down. And that's what will happen. Now, let me show you again the saddle. So here's the typical picture in 3 dimensions you would take with your camera if you were to go up a saddle and go down. Now, what I have up there is what is called a contour plot, which, again, you will know if I just pick the heights, all the points of the same height, then the typical saddle means that in one direction, let's say the solid ones that I'm thinking of, that's a peak, and it comes down to something less black and then goes up again. In the other direction, it goes from very white, which is in the valleys, and climbs up and drops down to the other side. Now, if I had such a saddle and I placed a marble on the very saddle point right in the middle, then, of course, as I showed in this particular case, where all the directions it was flowing away, it's going to certainly run down. And that's an intuition we would all observe, that the marble would not be stable at that point. Now, what is remarkable is that in many, many very different, again, contexts in physics, engineering, and so on, things are stable at a saddle. Now, how does that come about? Now, in this one, suppose I took this parabola with a saddle. In one direction, it's stable. In the other direction, it's unstable. But instead of having it just static, I put it on a turntable, like the old gramophone record days. You had a turntable, and you spun the turntable around, or a merry-go-round. Then you will find that, indeed, if I now place the marble there, it can be stabilized at that point. Now, I won't go into any of the details of this, but take it from me that it's a very simple thing to understand how that comes about. And it comes about because you don't have just that potential surface, but you have some rotation that you're talking about, that you're introducing into the system, and together they will give you a stability. Now, that stability is extremely important. And as I said, it crops up in all kinds of situations. This is a kind of just a schematic that I showed you, and I related it to our walking on saddles when we go in mountains. But again, don't worry about the equations. If some students want to talk about it later, we can. But this idea of a stability at a saddle because of the rotations is something that comes up in many contexts. One of them is in a context which has nothing to do with mechanics at all. It's not marbles and saddles and so on, but it is in the idea of trapping charged particles. The same thing applies with electric and magnetic fields and so on, by which we can control charged particles. You find that if you had a saddle, then the particles cannot be trapped at the center of the saddle. But if you now introduce, in that case, it's not so much a rotation, but it is what we call a radio frequency electric field, which has a frequency to it, which again has a time aspect. Then you can get stability. And the person who invented this, a man called Paul, and the Paul trap, he got the Nobel Prize in physics many years ago, but that's a central thing now in many of our labs. In fact, the most accurate atomic clocks today, you've all heard of atomic clocks, are these so-called rubidium plus ion atomic clocks, which have places like the National Bureau of Standards in Washington, D.C., or Gaithersburg near Washington, D.C., and in Boulder maintain. And these are extremely important today in technology and in physics. There are many things that we do in physics because we can trap charged particles, and we can do it because of this introducing a time element into the picture. And together then, you can get a stability. Now, the same thing can happen in a cosmological context, and this is what is associated with what are called Lagrange points in something like the Earth and Sun or the Earth and Jupiter system. So let's first look at that top frame there. Imagine that big circular golden orb in the middle is the Sun, and think of, say, a planet. So in these terms, there's the Sun, and then there's a planet. Whether it's Earth or whether it's Jupiter, doesn't matter. Now, it turns out that if you look at the gravitational forces that are acting between the Sun and the planet and the new object that we'll talk about, then there are 5 points which are called Lagrange points. And if you look at the potential there, here are again contours. Say, for instance, you look at this point. It has that same feature that I just showed you of the contour saddle, that indeed it is not stable in all motions. But again, because there is rotation, planets are rotating around the Sun and so on, it turns out that these are points where you can have quasi-stability. Now, you have all heard of the James Webb telescope. The James Webb telescope has been a long time in the making. It'll be a real super-duper telescope, much, much more capable than the Hubble Space Telescope, which has already given us so much information about the universe. The James Webb telescope will be launched 2 Saturdays from today, on the 18th. And we hope everything goes well, because that is going to go and sit in what is called the L2 point. You will hear this a lot in the TV news, that it's going to go out to L2. If this is the Earth, L2 is about 1 million miles from the Earth. So unlike the Hubble, there's a lot more riding on this, because you won't be able to go and repair it or anything if anything should go wrong. So we all have to hope that on the 18th of December, when it is launched, and finally it reaches L2, it'll work. It'll completely revolutionize what we do in astronomy. And in terms of what we can see much further back to the early universe, which is what our chairman, for instance, studies. And so the James Webb machine is going to be at that L2. Now, nature itself has done that. And in particular, when we talk about nature, we talk not so much with the Earth, though it happens for the Earth too, but if you take the Sun and you take Jupiter, Jupiter is a much bigger planet than the Earth, then it turns out that there are again, so just think now that this is Jupiter, again there are the same Lagrange points, and it turns out that some objects have got naturally trapped in these Lagrange points. And these have been known for millennia, and they're called the Trojan asteroids. And again, in October, in fact, it's by a curious coincidence, just the day when I said that I would give this talk, was the launch of a space mission by NASA called Lucy, which is going to be a 12-year mission, and that is going out to the Trojan asteroids. It will visit many of those asteroids which are sitting here, and they have some very important information probably about the early solar system that we can learn. And so this is what the Lucy mission is going to do, and here's just a picture of that. So this is the Sun in the middle. This is the orbit of Jupiter outside. This is the orbit of Earth here. And when it was launched, and then the various loops it's going to make, but it's going to visit some Trojan asteroids. There are on either side, and again, millions of kilometers from Jupiter and from the Sun, and it'll visit it and sort of take close-up pictures and other measurements and so on of these asteroids. So that's another mission which is related to this idea of stability at a saddle, which at first sight, as I said, you might not expect, but it comes about because of this added element of a rotation. Now, I'll take just 2 minutes to flash for you something which comes closer to my own research work, and that is now a sudden jump from thumbsticks on that cosmic scale. If I think of a very simple atom, now we all know that an atom has some kind of positive charge nucleus, and then there are electrons around it. If I take an atom with just 2 electrons, it's the helium atom, as many of you will recognize, then it turns out that if you look at the potential, now this has nothing to do with gravity. This has to do with the charged particles acting, and this is a quantum physics problem, whatever it is. But again, if you look at the potential of it, and again, without going into any details, notice that there are deep valleys where the electron, so to say, is very close to the nucleus, one or the other electron. There are 2 electrons, and therefore there are 2 deep valleys. And then there's a very big peak, which is when both electrons are on top, and as you know, like charged particles will repel. But then there is a saddle right in between. And it turns out that there are states of the atoms, like helium and other 2-electron atoms, which actually reside in that saddle. So I think the next slide is a contour plot of the same. So the saddle is right in the middle, and as you can see from the contour, it's very similar to what I had with the gravitational Trojan asteroids and the L2 that I talked about, but it's the same thing. And there are states which reside at that saddle. Now, of course, you don't really need to see this is on its side anyway, but the basic idea is actually very interesting, and it has to do with something that, again, is a lay term that some of you will have encountered. It has something to do with what is called the Coriolis effect. It's the Coriolis effect which deflects, for instance, air masses. This is why when you see a hurricane in the northern hemisphere, like the ones that come here, like Ida recently, they're rotating in a counterclockwise manner. Because as the air flows away, say, from the equator towards the pole, it's going to get deflected to the right if you're in the northern hemisphere. And that comes about through something called the Coriolis force, which is because the Earth is rotating. And that is the reason why you get a sideways deflection. So you're moving like that, but you get a sideways deflection. And this picture is simply to show how, even though that point may be unstable, as shown by the green arrows which are going out, if you have some kind of deflection like that to the side, then you can get something which is going to drive you back to that point, and so restore you to that point. And there you can sort of get a picture of the stability. Now, it's actually a little more subtle than that, because my quantum mechanical problem of the 2-electron atom has no rotations or anything like that. There is no time, in fact. It's just a static helium atom. It has these states.